Sir.
Okay, so can you hear me now?
Yes, sir. So you record this this class, right?
Yes, I'm recording.
Okay, sir.
Yes, so we have been looking at this particular question last time when before we left. Okay, so let us move back to understand what the question is saying. Okay, so here we are told that consider a steam power plant that operates on the ideal Rankine cycle. So the steam enters the high pressure turbine at 7 megapascal and 550 degrees Celsius and leaves at what? Saturated vapor. The steam is then reheated to 500 degrees Celsius. So here we have the cycle is given. You see, so the cycle is this that I have already sketched. So the fluid enters the turbine at this state, and then it is expanded and then reheated again. So the reheating temperature is 500 degrees Celsius. Okay, so ultimately we want to determine the specific specific enthalpy at each state. And I think we have already started, okay, to find the specific enthalpy. We have already found H1, we have found H2, so we need to find H3 and so on and so forth up to state 6. All right. So now we need to also determine the pressure at which the reheating takes place. Okay, so for reheating means we want to find the pressure, the operating pressure at P5 or P4 is the same as P5. We need to find the pressure at that state. Okay, so that is for the second question. And then number 3, so this should be like this. Yes, so question number 4, we were told to find the mass flow rate of the working fluid or the steam. Okay, so we have to determine that one as well. Okay, so we have also sketched the TS diagram for the whole cycle. Okay, this is the TS diagram for the cycle. So start from state 1. So normally when you are told that an ideal Rankine cycle, okay, ideal Rankine cycle, the fluid always enters the pump at saturated liquid state, and this saturated liquid state, and then it is compressed into the compressed liquid state before we continue with the heating process. So up to state 3, and then the fluid is expanded in the turbine. Okay, then we have reheating, okay, in the before the fluid enters the second turbine, and then we have expansion again. Okay, so these are the properties that are given. Now we have already determined H2. Now we need to find H3. Okay, so before we need to first look at state 3. So at state 3, what do we have? State 3. What are the properties of the fluid at state 3? We are told state 3, P equals to 7 megapascal and T equals to 500 degrees Celsius. So these are the two properties of the fluid which is necessary to determine all other properties. So P equals to 7 megapascal, which is 700 kilopascal. And T3 also equals to, let me see, is it 500? It is 550. 550. So this is 550. 550 degrees Celsius. All right. So now we need to find H3 and so on and so forth. Okay, then S3. So find H3 and S3. Okay, so from the table, first thing, before we can determine the state of the fluid, we need to find out, is this saturated or superheated state? So let us find the T saturation at the given pressure. Okay, at the given pressure. Okay, at 7 megapascal. Okay, so if you look from property table, this gives me 285.83 degrees Celsius. Okay, so looking at the temperature, T3 is greater than what? T saturation. So this implies state 3 is what? Is superheated vapor. Okay, so we will go to the superheated vapor property table. Okay, from table A6. Okay, so at 7 megapascal and 550 degrees Celsius, we will have H3 equals to 353.1.6 kilojoules per kilogram. And S3 gives me 6.9507. Okay, so kilojoules per kilogram. Okay, per Kelvin. So now, all that we need to do is to move on to state 4. Okay, so now at state 4, what do we know at state 4? Let's see. See, all that we know at state 4 is that the entropy, so this is temperature, TS diagram. TS diagram. Okay, so this tells us that S3 equals to S. So S3 is the same as S4. So we have temperature here and entropy. So S3 equals to S4. Okay, so that's the only way we can find H4. Okay, and then also P4 and P5 are the same. You understand? So we will continue from here and say that S3 equals to S4, which equals to 6.9507 kilojoules per kilogram. All right. And so the pressure over there, we will discover the same pressure. Let me see over here. Let's see over here. So, oh yes, we want to determine the pressure at which the reheating is done. Okay. So then we know that this particular state 4, this is saturated vapor state. Okay, so let's look in the diagram. See, so the steam enters the high pressure turbine at 7 megapascal and leaves at saturated vapor steam. So it leaves at saturated vapor. So means state 4. This state 4 is saturated vapor state. The steam enters at this particular condition and leaves at saturated vapor. Okay, so this is very clear. So saturated what? Vapor. If this is saturated vapor, then it means that the pressure that corresponds to this particular state, okay, will give us something like this. Let's see if I plot either the TS diagram or HS diagram. Okay, so we will have, let's see, or I'll draw the P. Let me see over here. So we are looking for the pressure. Let me see. Yes, so this is our constant temperature line. Okay, so we are looking for the pressure. Since we know that the pressure, the state is saturated vapor state, it means that the pressure at this particular state is going to be the saturation pressure, okay, at a given temperature. All right. Alternatively, we can also conclude or take note of the fact that if we know the enthalpy at this state, then it will help us to determine the pressure and at that particular state as well. So, but we know the entropy. So the entropy is given by this. Okay, so if we go to the property table, okay, so the enthalpy at this particular state, Hg, or the entropy, Sg, at this particular state, okay, so we don't know. That we need to determine. So cleverly, we will go to the property table and select a range, okay, and let me see. I don't know if you have, if you have your property table with you, if you open to table A5. So on table A5, yes, on table A5, here we need to somehow do some interpolation over here. table A5. Then we take some pressure range between P4. So let's say I take 3 to 5. Let's see. At pressure of 3 to 5, the entropy at a saturated liquid state. So let me just write, I'll explain. Let me just write this thing down for you. So I'm looking for the entropy now. So 2728.6. So by relying on interpolation, we will have, let's say, P kilopascal, and then SG kilojoules per kilogram. I'll explain. So this is enthalpy, kilojoules per kilogram. All right. So now I'm taking this pressure. So 3 to 5. So let's say P4 is what I'm looking for. I don't know. Okay. So, but I know the enthalpy at this state at 25 degrees Celsius, the entropy there is 6.965 kilojoules per kilogram per Kelvin. And then, yes, per Kelvin. So we have here 27 to 8.6. And at this pressure P4, we know that, you see, this S4 is the same as SG. Let's see. So let me see. S3 equals to S4 equals to SG. Okay, SG at the given pressure. So, but we know that SG to be this. This equals to 6.9507. So I'm going to write 6.9507. Then the corresponding enthalpy H4 is also not, we don't know. So then we will select again another pressure. So say a pressure which is a bit lower from this 3 to 5. Okay, so let's see over here which one I can select. So from 3 to 5. Okay, 3 to 5, then let's say the enthalpy Hg. So if you have your property table, you can refer to 7. So I'll take 350. So at a higher pressure, so 350. So now the corresponding enthalpy for 350 kilopascal, this gives me, the entropy at this state gives me SG is equivalent to, let's see, yes, 6.9, 6.9. So this gives 6.9, and then 402. And the corresponding enthalpy also, that gives 27 to 732 point what? 0. So we need to carry out interpolation with this. Okay, so for the interpolation, that gives us let's see. So in order to carry out the interpolation, so let's see how. So here we are interested in P. So P4 and H4. So we can use the interpolation for P4 first and then move on to H4 this way. Okay. And let's see. Okay. So then let me use my calculator to find this. So here I'll have P. Let me see. I'm going to use this first. So 350 minus P4. So 350 minus P4 divided by 350 minus, let's see, 325. 325. So this gives me, can somebody solve this for me? So 6.9402. So I have 6.9402 minus 6.9507. 6.9507 all divided by so 6 point again minus 6.9650. Okay, 6.9402 minus 6.9505. Sorry, 9605. 9650. 9650. Can somebody find P4 for me over here? What is, if you have a calculator with you? Okay. So let me see if I can use this. So 1 minute. Can somebody, Iman, can you help me calculate this?
I got 339.4.
Wait, I'm coming. Wait, So 1 minute, I'm coming.
Okay, sir.
Just to confirm. Let me see. Yes, Iman, what did you say you got?
I got 339.42.
339.42. Okay, so then correct. We need to find also the H4 now. Okay,
Where the slide, sir?
Okay. So I'll show you the slide now. Sorry. Wait 1 minute. So now, okay. So now we have it there. So we have 339.46 and H4. What did and let me write down the equation for H4. So again, H4 we will have. I'm going to use the same thing. This the pressure information to determine H4. So I have for H4 2732. So to find H4, I'll have 27, or in other words, let's say 350 minus P4. Let me see. Yes, we can use the same thing. We know P4 already. So we'll have 350 minus 339.46.
42, sir, not 6.
What?
42. 339.42.
Oh, 0.42, sorry.
Yes.
Okay, 339.42. All right, so 0.42. And then we'll have 350 minus 325. So this should be equal to, and now 2732. So 2732 minus H4, and then 2728 minus H4, again 2732 minus 2728.6. Okay, so can you solve this also? Let's see what is H4. If you solve carefully, I think you'll get something like 2730.56. Is it correct?
Yes, sir, correct.
Okay, so now let's move on. Good. So now we have found H4 and P4. Okay, so let me explain carefully again. You see, the thing is, we are told that state 4 is saturated vapor state. So knowing that it is saturated vapor state, then we know the what do you call it? The entropy at that state is given. Okay, the entropy at state 4 is given to be, the entropy at state 4 is this. Okay, S3 equals to S4. And this is the same as Sg because it is saturated vapor state. Okay, we know that value already. It is given by this. So that value is given by this. So it means the S over here, Sg, we know already. But Hg, we don't know the Hg. So what we will do is like this. So cleverly, we will write down P4, and its entropy is this. Sorry, the entropy, yes, is this. And the enthalpy is also given by this H4, which we don't know. So now I'm going to cleverly take, you can decide to take any range of pressure. Somebody can say, okay, I'm going to take, let's say, in the property table, somebody can decide to take a pressure range between, provided it is water property table. You go to the pressure column, okay? So you can take either, let's say, 400 and 450. Okay, so you come out with the same result. 400 and 450 means you put 400 here and 450 here, and then you put your P here. Okay, so but this entropy should be corresponding exactly to this P4. Okay, so then at 400 you find the entropy and enthalpy. Then at 450 you find the entropy and enthalpy. Then you do the interpolation. You come out with the same result. All right. So now let us move on to state 5. So now at state 5, let's see, state 5. So at state 5, we know now, so now, like I've told you, for this particular line, P4 and P5 are the same. In other words, the operating pressure, okay, for the reheater, they are the same. So what we will do is like this. We know P4 already. So P4 equals to P5. And what is it? 39.42 kilopascal. Okay. And then also T5 equals to 500 degrees Celsius. So now we need to find this state also. To find the enthalpy at this state, first we need to find T saturation. All right? Okay, we need to find T saturation at that particular state. But from the property table, we will discover that T5 is greater than T saturation at 339.42 kilopascal. Okay? So if this is the case, then it implies that it is superheated. So this implies superheated. Nice, superheated. Superheated. So superheated. Okay, so this will be superheated. So, so this implies superheated. So it is even clear that it is superheated because state 5 over here is always at the superheated state. Okay. State 5 here is always at the superheated state. Okay. So now, next, it seems to me, again, we need to do interpolation. So questions like this, you need to be very careful, extra careful. Okay, so from table A6, okay, from table A6, we will have, so interpolate between 0.3 megapascal and 0.4 megapascal. Okay, so megapascal. So we, and at 400, 500 degrees Celsius. So we will have okay. Okay, megapascal. So now we will have, so this is 500, not 50. It's 500 degrees Celsius. All right, so we'll have, for the interpolation table, I have MPa, I have the enthalpy, kilojoules per kilogram, and then the entropy, kilojoules per kilogram per Kelvin. Okay, so we are going to interpolate pressure 0.3. Okay, if you go to the property table, this is superheated. So 0.3. Then our existing pressure, okay, so this gives us, let's see over here, in megapascal, this gives me 0.33942 megapascal, and then 0.4. So I'm interpolating between these two pressures. Okay, so the enthalpy that corresponds to this is 3486.6, and this is H5. Okay, and then the enthalpy at 0.4, this is 3485.5, and then the entropy over here is 327. 8.327. So 8.3271. Okay, so then this is S5. So here again 8.1, 8.19, 8.1933. Okay. Excuse me. So from here, I would not like to waste my time. I'll just say that if you calculate between the enthalpies, we'll have H5 equals to 3486.17. So kilojoules per kilogram. And then the entropy, S5, also gives 8.2744 kilojoules per kilogram per Kelvin. Okay, so just a shortcut from the interpolation, this is the result. So now at state 6, so that's the last one. At state 6, what do we know at state 6? We know the pressure P6 equals to 50 okay, kilopascal. And then S6, let's see, S6 and S5, S6 equals to S5. Okay, so in a similar way, we have S6 or X5 equals to S6, and this gives me 8.277, sorry, 8.2744. 8.2744. 8.2744 kilojoules per kilogram. Then, so also we need to determine the enthalpy at this state. How do we determine the enthalpy here? Here we know the pressure, we know the entropy. We need to find Sg and Sf at a given state. Okay, so if you do that carefully, S6 was always greater than Sg at the given pressure, at a given enthalpy. Okay, so at a given entropy, that is 7 point, so 7 point, Sg at 7, that gives me 7.5931 kilojoules per kilogram per Kelvin. Okay, so this Sg, the Sg is this. This is Sg. And this is S6. So S6 is greater than Sg. You understand? So if that is the case, so it means the fluid is in superheated state. So it means state 6 is in the superheated state. So it means we need to draw this diagram again. It should not be on the saturated vapor state. It should be on the superheated state. Okay, so if you go by the drawing again, we'll discover. So we will have so on the TS diagram, okay, so we have this, and then we have this also. Okay, so first we have expansion in the first turbine. Isentropic expansion is this. Okay, so then we have reheating, and then followed by the second expansion in the turbine. So this is 1, 2, 3, 4, 5, and 6. Okay. So now what we will do, we know that state 6 is superheated. So clearly we'll go to the superheated table. But again, we need to do interpolation. So how do we do interpolation? We know we know the pressure, we know the entropy at that particular state. Okay, so we're going to do interpolation from table, let's say table A6, okay, from table A6 at 0.05 megapascal. okay, 0.05 megapascal, 0.05 megapascal. We will have, we know the entropy, okay, H kilojoules per kilogram, and then the entropy, kilojoules per kilogram per Kelvin. Okay. So we don't know H6. We are interested in H6. That's what we don't know. But we know that the entropy at state 6, okay, is given by 8.2744. So the entropy over here is 8.2744. So means we have to go to the property table, and under superheated table for 0.05 megapascal column, we need to find the enthalpy which is lower than this, slightly lower than this. Then we're going to write its value. So I'll take 8.1592, and its corresponding enthalpy is 2877.8. Similarly, an entropy which is greater than this, 8.3568. Okay, so then its corresponding enthalpy 297.6.2. So finally, if you calculate this carefully, you discover H6 equals to 2935 kilojoules per kilogram. Okay, so now we are almost done. The rest is just minor calculation. So to find the net specific heat input, so I. So net specific heat input. So input. So the net specific heat input comprises two. Where is the diagram? Yes. So we have one heat input over here. There will be one heat input from this section. So heat input from state 2 all the way to state 3. And then there will be another heat input for reheating from state 4 all the way to state 5. So we need to consider these two situations. So it means the total Q in, the net heat input is going to be Q 23 plus Q 45. Okay? So now that's what we are going to write over here. So that gives me Q in equals to Q23 plus Q45. And this is nothing, is equal to H3 minus H2 plus H5 minus H4. Okay. And if you slot in all the parameters, we will have 3531.6 minus 347.698 5. Okay, so plus again 3, 4, 8, 6.17 minus 273, 0.56. Okay, so if you calculate carefully, Q in equals to 3936. Sorry, 3939 again. 3939.51. Okay, kilojoules per kilogram. So now we need to find the mass flow rate of the steam. Mass flow rate of the steam. So IV, mass flow rate of what? Steam. So the mass flow rate of the steam can be calculated. You see, if we know the power input. Okay, so basically, mass flow rate of the steam can be calculated from Q in dot equals to mass flow rate dot times Q in. Okay, so this Q in we know already equals to 55, yeah, times 10 raised to the power 3 kilojoules, right? Sorry, kilowatt. I'm very sorry. So kilowatt. So this is kilowatt. And similarly, so M equals to Q in divided by small q in. So this is the specific heat input. So this gives me 55,000 divided by 3939.51. So if you calculate this carefully, it gives you 13.96 kilogram per second. Okay, so now the net specific work output. So net specific work output Okay, so will be given by W net equals to the W for the turbines, W total for turbine, W total for turbine, minus W for the pump. Okay, so W total for the turbine is equal to W turbine number 1 plus turbine number 2. So that gives us W turbine number 1 plus W turbine number 2 minus W for the pump. All right? So now eventually we will have W net equals to H3 minus H4. All right? Plus H5 minus H6 minus W pump. Okay? So if you solve this carefully, you will arrive at W net equals to 1344.94 kilojoules per kilogram. Now, the next thing is to determine the net heat loss at the condenser, okay, to the cooling water. Okay. Sorry. So we have been. So net heat loss at condenser cooling water. Okay. So this is very important. So let me draw the condenser for you to see. The condenser, you see, we have the fluid coming from the turbine. Okay. Okay. So this is the hot fluid. Oh, let me use a different color. Yes, so let me use a different color over here. Assuming this is the condenser. And then we have the fluid coming from the turbine. So the fluid enters these tubes and then goes away. And then we have the cooling water. Cooling water, the fluid from the cooling water. So for the cooling water, we have this. So it fills the whole of this space. And then it goes out. Okay, so we want to know that the amount of heat loss by this hot fluid equals to amount of heat gain by the cooling water. That's one thing we should know. Okay, so we can say like this that Q out for the condenser equals to mass flow rate of the steam times Q out. Okay. So this is very important. But we know also that for Q out, we have also defined Q in the, let me see over here. Q out equals to Q in, or in other words, so the network output, W net. Okay, so W net output, we should know W net, sorry. So W net output is equal to Q in minus Q out. That gives us Q in minus Q out. Okay. So it means from here we can easily calculate our Q out. Okay, but I know my W net is the same as mass flow rate of the steam times specific network output. Okay, so then this should be equal to Q in minus Q out. So I'm interested in Q out from here. So it implies Q out equals to Q in minus what? Mass flow rate times W net. So from the equation, we will discover that Q out is nothing equals to 55,000 minus 13.96 mass flow rate of the steam times the enthalpy. Sorry, the specific network 134444. Okay, so let me write it carefully, clearly. One three four four 0.94. Okay, so 0.94. Okay, so if you calculate this carefully, Q out is nothing equals to 36224.64 kilowatt. All right. So from here, this is the only way we can find our Q out. Q out means the net heat loss by the condenser. Okay. So now we want to find the minimum mass flow rate of the cooling water. So you see here, we have cooling water, mass flow rate of cooling water in, mass flow rate of cooling water out. So we want to find the mass flow rate of this cooling water. But by definition, Q out can also be defined as mass flow rate of cooling water times the specific heat capacity, Cp for the cooling water, or the C for cooling water, Cp for cooling water, times delta T, means the difference in the inlet and outlet temperature. Okay? So now, from this equation, we know Q out. So mass flow rate for cooling water is going to give me Q out, which is 36224, okay, 0.64, all divided by. Now, Cp for water is giving 4.18 kilojoules per kilogram per Kelvin, or degree Celsius. Okay, into bracket, the difference in temperature. So be careful over here. Now, how do we determine our delta T? We are told that the cooling water from the cooling tower enters the condenser at 28 degrees Celsius. Okay, at 28 degrees Celsius. So means for this delta T equals to T out minus T in. Okay, so here we have T in is this, and this is T out. Okay, so T inlet is equal to 28 degrees Celsius. How do we find T outlet? Since the operating pressure of the condenser, equals to 50 kilopascal, we need to determine the saturation pressure. Sorry, the saturation temperature at this pressure, and that corresponds to T outlet. Okay, so we will mention over here T. So T outlet equals to T saturation at the given pressure at 50 kilopascal, and this equals to 81.32 degrees Celsius. So therefore, our mass flow rate for cooling water equals to 3622.4.64, all divided by 4.18 times, let's say, kilojoules per kilogram per degree Celsius. And then I'll have 81.32 minus 28, degrees Celsius. Okay, so eventually mass flow rate equals to 162.53 kilogram per second. Okay, so that is the end to this particular question. Okay, so is there anybody with any questions so far?
No, sir.
Okay, so if there is no question, then I think we will have to stop over here. Okay, so some of you have started asking me questions related to the assignment. Okay, so now the only thing I can do is to maybe contact you online and then try to explain to you. Okay.
This is